Okay, thanks. Yeah, 12. We'll make a start. So, calculating the amount of energy from a thermochemical equation. Sort of done a little bit of this. E equals delta H by N. E is the amount of heat energy, or lowercase q, either way. Delta H, change in enthalpy. N, amount of substance. Don't forget about the coefficients. And remember, when we're calculating energy or heat, it's as a scalar quantity, right? If we're calculating delta H, the sign is needed. Cool? So that's that distinction between the two. So heat or energy released or absorbed, scalar quantity, non-inclusion of a sign. Delta H, yes, we include the plus or the minus. Minus is what sort of reaction? Exothermic, awesome. So therefore, positive delta H is endo. Here we go, let's have a look at this. Tungsten carbide reacts with oxygen according to the following equation. 2Wc plus 5H2O gives 2WO3 plus 2 CO2. Delta H is negative 2388. What do I notice about that equation? Or another way to ask that question is, how do I read this chemical equation? How do I read that? Yes, left to right. Okay, cool. All right, we're getting somewhere. How else do I read that? Products, reactants, cool. All right, we're getting somewhere. Yeah? Right, I'm noticing this. Yes? So I read this as if I'm saying 2 mole of tungsten carbide gives me this amount of energy. Yeah? That makes sense? So what would 1 mole of tungsten carbide give me? Half of this. Awesome. Calculate the amount of heat that would be evolved by the complete reaction of 1.125 kilos of tungsten carbide. What else am I reading in this question? Mass. All right, I'm reading the mass, and what do I need to do with that? I need to convert to mole, but what do I need to do with that first? Grams, thank you. So what is 1.125 kilos in grams? 1,125. Awesome. Okay. Where's your best friend, or back of your textbook? What is the molar mass of tungsten? Yeah, I picked this example for the reason that it's not a common example, right? Don't really see tungsten very often. 183.8. So therefore, we add 12 to that. Yeah, so we get 100 and... what was it, 183? So we get 195.8 as the molar mass of this. So 1125 divided by 195.8 will give us whatever. Yeah? So 1125 grams, number of mole of tungsten carbide, 5.74. Then delta H times N, I'm dividing by 2 because 2 mole gives me this, so therefore 1 mole gives me half of that. Gives me 6,860 kilojoules, or we could write that as 6.860 megajoules, or we could write that as 6.860 times 10 to the 3 kilojoules in scientific notation. Yeah? So I'd accept any of these 4 responses. 4 significant figures because in our question, 4 significant figures in the question. Yeah? Q equals MC delta T. This links in with practical 3.1.2. Q, amount of energy. M, mass of water. That's predominantly what we're going to look at. C, specific heat capacity of water. And the change in temperature, final minus initial. Or really, it's if we're cooling, we still want it in a scalar quantity, right? So it's not necessarily final minus initial if it's a cooling reaction. If it's exothermic, then yes. Oh, it's a heat of combustion anyway, so final will always be higher. So what do we need to do with the water? If we measured in milliliters, what do we need to do with that first? Not to liters, no? Mass of water, right? We need to convert it to grams. How do we do that? What's the density of water? Not 1. 0.997, thank you. If it's in the data book, we need to use it, right? So the volume of water is given in a calorimetry or a combustion question. We must convert it using that figure. Yes, there'll be only a marginal difference between the two. 0.997 and 1 is very close. But if it's not in, because it's in the data book, right, we need to assume that those questions we need to use it. Yeah.
Because it's data book, it says it's at 25 degrees, if it's at 20 degrees.
Doesn't matter. Still going to use that negligible difference. It's only 1 gram per mil at 4 degrees C, right? So as you get slightly cooler and cooler, that, is progressing closer and closer to a density of 1. But irrespective of what temperature it says, we're going to assume 0.997. So this is what we did in our prac. We measured the mass, or we measured the volume, 25 mil, and converted that to mass. So if you want to talk about errors, hint, right? You measured the volume of water, you didn't measure the mass. And we also have uncertainty in the amount of volume that you measured. And there's more uncertainty in that measuring cylinder compared to the electronic balance. So had we used the electronic balance, we actually reduced the amount of uncertainty in the mass of our water. But the greatest source of error in that prac was heat loss to the environment. And what we can do is look up in your data books or online, you can look up the theoretical or literature value of the combustion of your different fuels, right? And then make a comparison between your calculated value and the value obtained under controlled other conditions. And you'll find that there is an enormous disparity between your results, because the best thing about this prac is the discussion of error, because the instruments we're using actually have a pretty low level of uncertainty. Right? The electronic balancers are highly accurate. The thermometers are pretty good to the nearest 0.25 of a degree or whatever. Right? So they're pretty accurate pieces of equipment. We've got very low uncertainty, but a very large margin of error because of that enormous loss of heat to the environment. And the other things that weren't controlled. How high the test tube was away from the flame. The fact that it wasn't a bountiful supply of oxygen, in which that it wasn't a complete combustion, and so on. We could look at the differences in amount of error depending on the fuel. So we expect that methanol would probably have a greater chance of complete combustion than, say, propanol. Propanol requires a greater amount of activation energy in order to break the bond. So it's likely that propanol is going to combust less readily than methanol will. And we probably would have seen that in our results, that the temperature rise of the water was much faster with methanol than the other fuels, despite the greater the hydrocarbon chain, the greater the energy density. Let's have a go at a question like this. So this could have been your results. You used 25 mils of water. This question gives us 100. 0.355 grams of methanol undergoes complete combustion in spirit burner, heat of energy released, heats 100 mils of water, temperature rose from 20.24 to 37.65. Now we can go through the calculations. I'm happy to do that. But let's just consider what figures do we have and what do I need to do with them. 0.355 grams of methanol. What am I going to do with that? I'm going to convert that to mole, aren't I? Yeah? I've got 100 mils of water. What am I going to do with that? Turn it to grams. What am I going to do with the change in temperature? No, I don't need to convert to Kelvin, because the change in Kelvin will equal the change in Celsius. I don't need to do a conversion. I only need to do a conversion, right, when I'm talking about gas loss, not talking about gas loss. So final minus initial. Cool. So Q equals MC delta T. I'm calculating the amount of energy first. 100 by 0.997 gives me my mass of water times 4.18 specific heat capacity of water times 37.65 minus 20.24. What do you get? I'm going to do it on the board. Oh, I've got the slides next. Just want you to work through it. Yeah? You with me? Do you need me to write? Let's pause it. I'll write it. Cool. And there we go. Mass of water, mass of the fuel, temperature change of the water gives us that. Q equals MC delta T. Calculate the number of mole of water, of the methanol. Heat of combustion is the energy divided by number of mole. Notice I haven't included a sign because it's heat of combustion, not enthalpy of combustion. Or it's not asking us to write a thermochemical equation. So I'll get you to do that as an extra question. Write me a thermochemical equation for the complete combustion of methanol. Off you go.